Imagine receiving a signal from space. Not unusual, not constant, but something slow, repeating, like a heartbeat in the dark. For decades, we believed space signals followed certain rules, fast bursts, predictable patterns. But then, something changed. Scientists began detecting signals that didn't fit anything we knew. Signals that appeared, paused, and returned again minutes later. They called it the LPT anomaly. But what exactly are these signals? A new type of cosmic object? Or something we still don't understand? Because in a universe this vast, not everything follows the rules. Welcome to Curiosity Rift.
Deep in the Milky Way, something is broadcasting. It isn't the chaotic static of a dying star or the rapid-fire chatter of a typical astronomical event. It is a signal repeating with a slow, deliberate, and unyielding rhythm. Astronomers first caught wind of this phenomenon using wide-field radio telescopes, scanning the skies over the remote Australian outback. These massive arrays pull down huge swaths of data, and hiding inside those recent observations were strange sources, cataloged as GLEM XJ1627 and GPM J1839-10. When researchers isolated the signals, they found massive, highly polarized bursts of coherent radio energy. These were incredibly bright, highly organized radio waves that blasted out into space, with some bursts lasting up to 5 full minutes. The signal from GPM J1839-10 arrives with absolute clockwork precision. Every 22 minutes, without fail, the transmission repeats. Most of the radio sky is defined by frantic millisecond flashes or unpredictable eruptions. A steady 22-minute repeating pulse behaves more like an artificial beacon, the exact kind of regularity that triggers a formal SETI analysis. When you find a pattern like this, the immediate scientific reflex is to look backward. Astronomers began digging through decades of archival data from global observatories, like the Very Large Array, to see just how long this object had been active. The archival hunt was successful. Historical records showed that GPM J1839-10 had been transmitting this exact 22-minute pulse since at least 1988. For 33 years, a continuous, rhythmic cosmic heartbeat had been striking Earth. It went completely unnoticed because our search algorithms were trained to catch rapid-fire ticks, leaving us entirely blind to a signal this slow. A signal persisting with perfect regularity for over 3 decades forces a reckoning. Either researchers had stumbled upon the most patient artificial beacon ever recorded, or the existing models for how stars age and die were simply wrong. To understand why this discovery is so disruptive, we have to look at the death line. It is the mathematical threshold that dictates whether a star has the physical capacity to emit radio waves. Normally, radio signals come from pulsars. These dense neutron stars generate massive radio beams by spinning incredibly fast. But as a pulsar ages, its spin slows down. Once it crosses that threshold line, it loses power and goes dark. GPM J1839-10 rotates only once every 22 minutes. According to our current understanding of neutron stars, this object is far too slow to generate any radio emission at all. This comparison shows the star's available rotational energy versus the actual energy output of its 5-minute radio bursts. The power required to broadcast those signals exceeds the total energy the star could possibly generate from its spin. Rotation cannot be powering this beacon. The math doesn't add up, pushing the tension between a natural anomaly and an intentional technosignature to its absolute peak. To rule out an artificial source, researchers look at the frequency. An intentional alien broadcast would likely use a narrow, specific band of frequencies to pierce through the static. This signal, however, is broadband radio noise, the hallmark of a natural high-energy process. That leaves astrophysicists with 2 natural explanations. The first is the ultra-long period magnacar. After a supernova, a ring of debris fails to escape the star's gravity and falls back onto the surface, acting like a brake that slows the star's spin to a crawl. In this scenario, the massive radio waves aren't powered by the spin of a failing star. Instead, they are fueled by the decay of an impossibly strong, twisted magnetic field, releasing energy into space. The second possibility is a binary model, the white dwarf unipolar inductor. This involves a highly magnetic white dwarf locked in a tight orbit with a red dwarf. As it spins, its magnetic poles slice through the solar wind. It acts like a colossal dynamo, shooting out a radio pulse every time it aligns with Earth. Whether it is a decaying magnetic field or a cosmic dynamo, these mechanisms prove that the universe can naturally construct beacons that perfectly mimic artificial precision. For decades, we operated under a narrow assumption. The universe only spoke in frantic, second-long flashes. We were simply deaf to the slower rhythms playing out in the dark. Long-period transients prove that stars we once labeled dead can remain active for decades longer than our theories predicted. The galaxy isn't a graveyard of silent stars. It's a landscape filled with hidden, rhythmic heartbeats. We finally learned to listen at the right speed.
The LPT anomaly challenges what we thought we knew about the universe. Slow, repeating signals coming from deep space with no clear explanation. Some theories suggest unknown neutron stars, others point toward entirely new cosmic phenomena. But the truth is, we're still listening, and we still don't fully understand what we're hearing.